Hello, and welcome to Linear Algebra. This is lecture 39. We'll be talking about linear differential equations. So, last time, we talked about the Jordan canonical form. So, this is the next best thing to diagonalizing a matrix. Every matrix, when you're working with complex coefficients, is similar to a matrix that is in Jordan canonical form. If the matrix is diagonalizable, then the Jordan canonical form is the corresponding diagonal matrix. This time, we're going to talk about some applications to differential equations. Okay, so we've talked about derivatives in this class. We've seen that the derivative is a linear map. Right, so say from smooth functions on the real line to smooth functions on the real line. With eigenvalues, all real numbers, right? So in fact, the eigenspace corresponding to a real number is just the span of the exponential function e to lambda t. In terms of differential equations, we could look at the equation y prime of t equals lambda y of t with some initial conditions, say y of 0 is equal to y naught, some fixed real number. Then this equation has a unique solution. Y of t is equal to y naught e to the lambda times t. Right, so satisfying the eigen equation means that you're in the eigenspace, so you're some multiple of e to the lambda t, and then this initial condition tells us which multiple of e to the lambda t. So next, let's consider a situation where we have several functions. Of one real variable. Well, let's just say one variable. And they satisfy a linear system now. Of first order differential equations. So we have something of this form. Let's say y1 prime is equal to a11 times y1 plus a12 times y2 dot 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 a1n yn. Similarly, y2 prime is going to be a21 y1 plus a22 y2 and so on till a2n yn. And one such equation like this for every y up to yn prime which is an1 y1 plus an2 y2 plus dot 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 up to ann yn. Right, and here let's assume that each of these coefficients, aij, is a fixed number, let's say a complex number. y1 through yn are functions of t, and their derivatives are related in this way. So since we have a whole semester of linear algebra under our belt, we should write this in terms of matrices and vectors. So let's say that we set y hat of t to be the function with coordinates y1 of t to yn of t. So this is a vector valued function. And then let's say that capital A is going to be an n by n matrix with complex coefficients, is the matrix whose ijth entry is little aij, the corresponding coefficient. So in terms of this notation, the system has the simpler form. A times y hat of t is equal to y hat prime of t. Right? A y hat prime of t, of course, just means the vector whose coordinates are y1 prime of t, y2 prime of t, and so on down to yn prime of t. And now, in analogy with what we did in one variable, given an initial condition, for example, y hat at 0 is equal to the vector y naught, which would be, have coordinates y1 of 0 down to yn of 0. So given an initial condition, then we'll show that the system y hat prime of t equal to a times y hat of t with initial condition y hat at 0 is equal to y hat naught has the unique solution, and is going to look just like in the case of one function. Y hat of t is going to be e to the t a y hat naught, right? But now, of course, this is a matrix, and we're taking the exponential of a matrix. That gives us another matrix. We apply that to this vector, we get another vector, and that vector solves this differential equation, but this differential equation. Okay, so let's check that this is true. So first, let's recall this matrix exponential, e to the ta this is the matrix exponential. It is defined by the series. So e to the ta is going to be identity plus, so the n by n identity plus t times a plus ta squared over 2 factorial, and so on. The kth term would be t times a to the kth power divided by k factorial, and so on. So it's a series. This series converges absolutely and uniformly on compact subsets, so we may differentiate it term by term. Right? That means that we can compute the derivative with respect to t of this exponential by taking the derivative with respect to t of each term and then adding up what we get. So derivative of the identity matrix with respect to t, of course, would just be 0. The identity of t times a with respect to t would be a. The derivative of ta squared over 2 factorial with respect to t would be 2 times ta divided by 2 factorial, and so on. The kth term, the derivative would be k ta to the k minus 1 over k factorial, right, and so on. And we recognize this. Well, we can pull out a common factor of a, either on the left or on the right. Let's pull it out to the left. Then we would get the identity plus, actually, let's pull out a common factor. Sorry, I did this wrong. This factor, I'm differentiating with respect to t, not ta. So the derivative of ta with respect to t is a. The derivative of ta squared with respect to t would be 2t a squared. And so on. Here, the derivative with respect to t would be k times t to the k minus 1, a to the k, and so on. Right, sorry about that. Okay, having done that correctly this time, now I can pull out a common factor of a on the left or the right. If I pull it out on the left, then I end up with identity plus t times a, and so on, with the kth term. Well, here this term would be t to the k minus 1, a to the k minus 1 divided by k minus 1 factorial, and so on. And we recognize this as a e to the ta. Right. On the other hand, we could have pulled out a common factor to the other side, right, on the right. And so this is also equal to e to the ta times a. So that's a nice property that we see here. A commutes with e to the ta. In fact, say also, the exponential of a sum of matrices is equal to the product of the exponentials as long as AB commutes with BA. AB is equal to BA, as long as A and B commute. In particular, e to the TA is always invertible with inverse e to the minus TA. Okay, so now having established this, let's go back to our differential equation. If we know that y hat prime of t is equal to a y hat of t, and y hat of 0 is equal to y hat naught, then let's consider c hat of t, the function e to the minus ta times y hat of t. Okay, so I want to show that the unique solution to this system is the exponential of a multiplying y naught. So the way we're going to show that is assume that you have any solution y hat of t to the system, and consider this function c hat of t, which is just take the exponential of minus a and multiply it with this. So e to the minus ta times y hat of t. this function satisfies, okay, take the derivative with respect to t of c hat of t. So by the Leibniz rule, this would be derivative with respect to t eta minus ta times y hat of t plus e to the minus ta times the derivative with respect to t of y hat of t. Okay, derivative with respect to t of eta minus ta, well, we just established that this is equal to minus a e to the minus ta y hat, well, and then times y hat of t. And then here we have e to the minus ta. The derivative of y hat with respect to t is equal to a y hat of t. And so we see that this is equal to minus a e to the minus ta plus e to the minus ta times a, all of that times y hat of t. And by what we just talked about, this is the same as this. So we get 0. Okay, so this function, z hat of t, we just checked, it doesn't depend on t at all, right? It's a constant, right? C hat of t is equal to C hat of 0 for all t. Right? Okay, but we know what C hat is. So that is e to the minus ta y hat of t, and then C hat of 0 is equal to e to the 0, that's the identity, and then y hat of 0, so this is just y hat naught for all t. And so y hat of t is equal to e to the ta y hat naught. Right? And so just as we expected, in analogy with the case of a single function of a single variable, the unique solution is just multiplication by the exponential. Okay, so now let's say that you're actually given such a system and you want to write down the solution. Okay, well, that's one way of writing it down. What if you want something a little more explicit? Well, maybe A is diagonalizable. If A is diagonalizable, let's say A is equal to S inverse with the diagonal matrix, then the kth power of A is, well, the kth power of this product. And if you write this out, and of course, all of these intermediate S inverse with S's cancel out. And we're just left with S d to the k S inverse. So similarly, e to the ta would be just S e to the td S inverse. Now here D is diagonal matrix, lambda 1 through lambda n on the diagonal, with those being the eigenvalues of A. So D to the k would just be the lambda 1 to the k through lambda n to the k on the diagonal. And correspondingly, e to the td would be a diagonal matrix with e to the t lambda 1 through e to the t lambda n on the diagonal. Okay, what does that tell us about writing down solutions of the differential equations? Well, if you have your differential equation, y hat prime of t equals a y hat of t, y hat of 0 is y hat naught, some fixed constant vector. Then, okay, y hat of t is e to the ta y hat naught. And we can write that as s e to the td s inverse y hat naught. So another way of saying that is that s inverse times y hat of t is equal to e to the td s inverse y hat of 0. Or, so let's say you write y hat of t with respect to a basis b made up of the eigenvalues. Then this is just transforming this vector by multiplication by e to the td's, which would just be scaling each coordinate by e to the t lambda j. So here with the eigenbasis of the matrix A. Okay, so here's another way of saying that. When A is diagonalizable, we can solve this system by writing our initial condition, y hat naught, as a linear combination of eigenvectors of A. Might say y hat naught is equal to v1 up to vk, with A times vj equal to lambda j vj. And then we can write down the solution. Y hat of t is just going to be e to the lambda 1t v1 plus dot 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 e to the lambda nt vn. Yeah, actually, these went up to k. The lambda kt vk. Right, so if you have this system of linear equations and the matrix A is diagonalizable, then it's easy to write down the solution to the equation. What you do is you take your initial condition, you write it in terms of eigenvectors of A, which you can do because A is diagonalizable, and then you're basically done. The solution at time t is just the solution at time 0, where you weigh each eigenvector by e to lambda jt, lambda j being the corresponding eigenvalue. Okay. What if A is not diagonalizable? Well, using a basis of generalized eigenvectors, you can get A into a block diagonal form. So now A looks like script A1, script A2, and so on, script AK, and then zeros away from those. So these, it looks like a diagonal, but now the diagonal entries are not numbers, they are matrices. But the exponential of such a matrix is this block diagonal matrix where now Each block is the exponential of the block we started with. Right, now choosing the basis carefully. A is similar to a block diagonal matrix involving only Jordan blocks. Right, remember we have notation J, L, M. So JLM is an M by M matrix. J lambda M is lambda times the identity plus NM, and here NM is a strictly upper triangular matrix whose ijth entry is either 1 if j is equal to I plus 1, so if we're right over the diagonal, and 0 otherwise. Okay, so then if we want to figure out the exponential of a matrix, in general, we have to figure out the exponential of these block diagonal matrices. And to figure that out, well, it's enough to figure out the exponential of a Jordan block. Okay, so what's the exponential of J lambda M? Well, fortunately, lambda times the identity and M commute. So the exponential of J lambda M is equal to the exponential of lambda times the identity times the exponential of NM, and that's just e to the lambda times the exponential of NM. Okay, so the only thing we need to figure out is what is the exponential of NM. Let's go ahead and put in the t variable. So what's the exponential of t times NM? Well, let's look at the first few cases. If m is equal to 2, then N2 is the matrix 0, 1, 0, 0. So if you square that matrix, you get 0. So then it's easy to figure out what e to the t N2 is, because you just write down the series and you get I2 plus t N2, and then you stop. All subsequent powers are 0. So that means that we have 1 t 0, 1, right? That's the exponential of N2. Let's look at the case m equal to 3. So N3, so it's a 3 by 3 matrix, and it looks like this, right? Zeros everywhere except immediately above the diagonal where you have 1s. So in this case, N3 squared is 0, 0, 1, 0, 0, 0, 0, 0, 0. And N3 cubed is 0 matrix. So again, the exponential is quick to write down because the series will stop very quickly. So we're going to get I3 plus t N3 plus t squared N3 squared over 2 factorial. And then we stop because starting at the cubed power, they're all 0. So that means that we can write this down. We have 1 and then t and then 1/2 t squared in the first row, and then 0, 1 t in the second row, and 0, 0, 1 in the last row. All right, and so you can see the pattern, and it's easy to check that this pattern continues. In general, e to the t and m is the matrix that looks like 1, 0, 0. Then this Next column starts with t and then 1, and 0, and so on. Then the next one starts with 1 squared t squared, and then t, and then 1, zeros, and so on. And then the last column starts with 1 over m minus 1 factorial, t to the m minus 1. Then the next entry is 1 over m minus 2 factorial, t to the m minus 2. Right, and so on until you get a 1. Okay, so those are the exponentials of the NMs. Multiplying it by e to the lambda t would give us the exponential of t times the Jordan block. And that all put together gives us the exponential e to the ta for any matrix A with complex coefficients. Just first put it into Jordan normal form. Okay, so great. So now we've seen how to solve a system of linear equations with constant coefficients using linear algebra. Next, let's look at a difference equation. I don't want to talk about these in general, although you'll easily see how it generalizes. I want to look just at one specific one because it is cool. Namely, let's look at the Fibonacci sequence. Right. So as you all know, in Leonardo of Pisa's book, Liberabaci, he talks about a sequence about the nth term of the sequence tells you how many pairs of rabbits you have, assuming that no rabbits die, that you start out with one pair of rabbits. Then at the next step, you still have one pair of rabbits. But at the second step, that first pair of rabbits has reproduced, and every pair of rabbits after 2 steps will start producing another pair of rabbits every step. So what that means is that an plus 2 is going to be an plus 1 plus an for all n. And so let's take this equation, this difference equation, and try to figure out a formula for the nth term in the sequence, right? So let's ask ourselves at the nth step, how many pairs of rabbits do we have? Okay, so let's put this into matrix vector form so that we can apply some linear algebra to it. So let's consider the sequence of vectors xn with coordinates an and an minus 1. Right? So our first vector x1 would just have entries a1 and a0. Right? In particular for us, that's just a vector 1, 1. Right? But you'll see that our computations would let us figure out how many pairs of rabbits we have as soon as we know how many we have at step 0 and how many we have at step 1. Right? After that, of course, is determined by the equation. Okay, so what is the equation for the vectors? Well, xn plus 1 would be an plus 1 an. And we can write an plus 1 as an plus an minus 1. Then let's leave an alone in the second coordinate. So we can write that as 1, 1, 1, 0, acting on the vector an minus 1, right? Which is to say that we have 1, 1, 1, 0 multiplying the vector xn. Okay, so this is our relation for the vectors, right? You get one vector from the previous one by multiplying it by this matrix, right? And this captures this equation we had for the entries of the vectors, right? So with A equal to the matrix 1, 1, 1, 0, we have xn plus 1 equal 8 times x n. So the sequence we have, the Fibonacci sequence, is a1 and then a times x1 and then a squared x1 and so on until we have a to the n times x1. And this would have coordinates a n plus 1, a n. Right? That's the same as a to the n acting on the vector 1, 1. Okay. So how do we compute a to the n acting on the vector 1, 1? Well, here's a. So you could just start writing down powers of a and try to find a pattern, right? But better to think about it first. When you want to compute a function of a matrix, what you want to do is diagonalize the matrix, and then it's easy because you just compute that function on the eigenvalues. So let's look at this matrix. Is this matrix diagonalizable? Well, it's symmetric, so it's guaranteed to be diagonalizable. In fact, it's guaranteed to be diagonalizable. It's guaranteed to have an orthonormal eigenbasis. Not that every eigenbasis will be orthonormal, but that there is an orthonormal eigenbasis. So let's diagonalize. So what are the eigenvalues? Eigenvectors of A. Okay, well, let's look at A minus lambda times I2. So this would be the matrix 1 minus lambda, 1, 1 minus lambda. Right, and so this, we're going to do row operations to try to figure out when this has non-trivial null space. So row operations, so let's switch the order of the rows just so that the first entry is a pivot. And then I can use that first entry to clean its column, which means that here I'm going to have 1 minus lambda times lambda minus 1. Okay, and that is in row echelon form. For this to have non-trivial null space, we need for the second column not to have a pivot, so we need 1 minus lambda times lambda minus 1 to be equal to 0. Right? So that means that lambda squared, so if we write that out, we get minus lambda squared plus lambda plus 1 is equal to 0. Right? So lambda is equal to 1 plus or minus the square root of 5 divided by 2. Right? So we have two distinct eigenvalues. All right, let's write them. Lambda 1 is 1/2 1 plus square root of 5. And then let's say that lambda 2 is 1/2 1 minus the square root of 5. Okay, notice the relation, I'll use this later, that 1 minus lambda 2 is equal to lambda 1. Now for either of these, right, I need to look at the eigenvectors. So for either of these, the reduced row echelon form of A minus lambda times the identity is just 1 minus lambda in the first row and zeros on the second row, right? Because that's how we arranged. And so the vectors V1 with entries lambda 1, 1, and V2 with entries lambda 2, 1 are eigenvectors corresponding to lambda 1, lambda 2 respectively. All right, so now I want to compute A to the n applied to the vector 1, 1. So let's write one as a linear combination of eigenvectors. So we could take advantage of orthogonality, or we could just write out directly, right? So let's say I want 1, 1 to be C1 V1 plus C2 V2, right? That means I want C1 lambda 1 plus C2 lambda 2 to be equal to 1, and C1 plus C2 equal to 1. So from the second coordinate, I get C1 plus, well, let's go ahead and say C2 is equal to 1 minus C1. Plugging that into the first coordinate, we get this equation, which is the same as saying that, equal to 1, which is the same as saying that lambda 1 minus lambda 2 times C1 is equal to 1 minus lambda 2. Hence, C1 is 1 minus lambda 2 divided by lambda 1 minus lambda 2. And C2 is equal to lambda 1 minus 1 divided by lambda 1 minus lambda 2. Okay, and a to the n applied to the vector 1, 1, right, is a to the n applied to C1 V1 plus C2 V2. So it's C1 lambda 1 to the n V1 plus C2 lambda 2 to the n V2. Okay, so now we can work out, just looking at the second coordinate, right, of the vector an times 1, 1, we find that the nth term of the Fibonacci sequence is equal to, well, this constant C1, so 1 minus lambda 2 divided by lambda 1 minus lambda 2 times lambda 1 to the n, plus the constant C2, so lambda 1 minus 1 divided by lambda 1 minus lambda 2 times lambda 2 to the n. Right, and that is lambda 1 to the n plus 1 divided by lambda 1 minus lambda 2 minus lambda 2 to the n plus 1 divided by lambda 1 minus lambda 2, right? And that is 1 over square root of 5 times 1 plus square root of 5 divided by 2 to the n plus 1 minus 1 minus square root of 5 divided by 2 to the n plus 1, right? And there you go, a formula for the nth term in the Fibonacci sequence, surprisingly involving square roots of 5, which, you know, cancel out because we know an is always an integer. But they show up because they're the eigenvalues, because they're parts of the eigenvalues of the matrix. In fact, this is the golden mean that's showing up here. So this gives us the Fibonacci sequence in terms of the golden mean. Okay, very good. We'll stop there.